Kimberly Sinclair. I'm from the University of Washington, Department of Earth and Space Sciences. I'm working with David Catling and Tim Elam. I'm going to talk to you guys about this project, the Mineralogy of Evaporites and Sediments in the Alkaline Phosphate-Rich Lakes of the Caribou Plateau, which is work I've been doing with Sebastian Haas and is funded by the Simons Foundation. Okay, so I want to give you a bit of background about the phosphorus problem in astrobiology, because I know we're all coming from very different backgrounds. There's a lot of biology talks this morning, though, so I'm sure a lot of you guys are caught up on this. But so we all know DNA on the right-hand side here has this sugar phosphate backbone, and then you have your base pairs. If you zoom in closer, you're seeing your phosphate group, your sugar, and your nuclear base here. And in order to get this phosphate to incorporate into the nucleotide, you need very high levels of phosphate. And this has been shown by research done by Pauner et al. In 2009. So this question we want to ask is how much phosphorus is actually available for prebiotic phosphorylation on early Earth? And even though we need these very high concentrations of phosphate, up to 1 molar in prebiotic phosphorylation experiments, we only see very low concentrations of phosphate in the environment, close to the micromolar level. And that's because in natural waters, phosphate will combine with calcium and fall out of solution as an insoluble mineral known as apatite or calcium phosphate before reaching very high concentrations. So there's a bit of a problem here, and that's what we call the phosphorus problem. We've proposed a solution to the phosphorus problem. In a paper by Toner and Catling in 2020, the hypothesis was stated that abundant carbonate leads to calcite formation, calcite being calcium carbonate, thus suppressing the calcium phosphate mineral formation and leaving phosphorus in solution to concentrate to higher levels. So in order to test this theory, we visited the most phosphorus-rich lake in the world. This plot on the right-hand side is from Toner and Catling 2020. You see very high phosphorus concentrations in these lakes on the top right side, which are good enough in Last Chance Lake. And so that's where we wanted to visit to understand why you're getting these very high concentrations of phosphorus. We can then apply our understanding of these lakes to possible analog lakes on prebiotic Earth where origin of life could have happened. So a little bit about these lakes. Last Chance and Goodenough lakes are carbonate-rich alkaline soda lakes on the Caribou Plateau in British Columbia, Canada. Left-hand side, you see the map of British Columbia here, and this green swath is the Caribou Plateau. It's right east of those coastal mountains, not too far north of Vancouver. If you were to zoom in on Google Maps, you would see the lakes here, Goodenough Lake here, and Last Chance Lake here. They both have very high phosphate concentrations, but particularly Last Chance Lake gets up to 37 millimolar of phosphorus, which is very high in comparison to that micromolar level that we're usually seeing in natural waters. And this is an image of Last Chance Lake taken in November 2021, which is what it looks like from the ground level. So you're seeing it form into these sort of brine pools. So a little bit of context from these lakes. They're two small, less than kilometer squared, shallow, closed basin lakes with sodium carbonate, sulfate, chlorine brines. These are typical major ions of soda lakes developed on basaltic rock. Their sulfate, potassium, phosphate, and magnesium are abundant, whereas calcium, iron, silicon, and dissolved inorganic nitrogen are present at very low concentrations. The salinity reaches up to 462 grams per liter, which is about 13 times seawater salinity, so they're very salty. And the pH ranges from 9.7 to 10.7 in both of these lakes, depending on the time of year and the location in the lakes, because they do get spring infed from surrounding rivers and such. Or sorry, from groundwater, not rivers. So we wanted to go and visit these lakes over different seasons in order to understand how the mineralogy of different precipitates and evaporites, as well as precipitates in the sediments, change. So we went in winter, summer, and fall, and you can see the corresponding pictures here. In winter 2021, you see these brine pools starting to freeze over. In summer 2022, it enters this ephemeral lake stage where it has enough water that it actually covers the entire surface. And then in autumn 2022, these brine pools are drying out into salt flats, and so there's basically no water left in this system at all. It's just salt. So we wanted to collect lots of different evaporites, which are these salts that are forming around the lake shore, as well as precipitates within the lake. These are different fun examples of evaporites we collected. So in our winter trip, you get a lot of these salts forming on rocks around the lake shores or around the brine pools. In June, this is an example of a precipitate that formed and fell to the bottom of the lake, and so you can pick it up from under the water. It's a lot of salt mixed in with mud and clay. And then in September, when it's in that salt crust phase, you can dig into the salt crust and take this out, and that's what the cross-section looks like. So you're getting these very white, opaque salts on the top, that middle layer of translucent natron salt in the middle, and then a layer of algae right above the mud. We also wanted to collect sediments from the lake bottom, and so these are pictures of us collecting different sediment samples with sediment cores. We did it both around the lake shore as well as at the lake bottom, and then the center picture you see is us taking those sediment cores and chopping off different depths in order to see how the mineralogy changes with depth in the sediments. So we did mineralogy analysis with X-ray diffraction. We used a Brooker D8 powder X-ray diffractometer with a copper anode microfocus X-ray source, which is the microfocus X-ray source is really useful when you have very small quantities of powder that you're trying to analyze. And a Pilatus 100K large area 2D detector is really helpful when you want to increase the resolution of your diffraction patterns. Just a quick note about sample preparation. We tried to isolate the mineral phases visually as much as we could from our samples in order to simplify the pattern matching. Grind it up really fine. You want to have good particle statistics for X-ray diffraction, and then dropping it onto a silica zero background sample holder to try and get that flat homogeneous surface that's so important. And then for those of you who haven't seen XRD data before, this is sort of what it looks like. You've got your 2 theta on the x-axis, intensity on the y-axis, and your observed pattern is in blue. This is using a software called GSAS2, which is an open source code for XRD analysis. And then you're trying to match database patterns of different minerals to this observed pattern. And so the calculated one pattern, that's a conglomeration of all the different mineral phases we've identified, is showed in green overlaid on top of that observed pattern. So this is an example of one evaporite and one sediment from these lakes. Going through on this evaporite here, we've identified multiple different sodium carbonate phases. So there's a lot of thermonatrite, which is sodium carbonate with one water molecule at the 60% weight percent level. And then for reference, in this sample here, the thermonatrite is this blue. And so each mineral you expect to see different peaks in the 2 theta range. And so we're just matching those peaks. We're also seeing trona, which is another sodium carbonate, as well as thenardite, sodium sulfate, halite, sodium chloride, berkite, which is a sodium carbonate sulfate, and nacolite, a sodium bicarbonate. So these mineral phases are all very common in these evaporites we're finding across these lakes. While in the sediment, we're seeing a lot of feldspars like albite, augite, as well as anorthoclase and anorthite in other samples, around the 70% to 20 to 30% range. A secondary phase we're seeing a lot of in the sediments is dolomite, which is that calcium magnesium carbonate. And that's very important, and I'll come back to that in a moment. We're also seeing a lot of minor phases like quartz and Vesuvianite and other things like that are just present in the natural soil in the area. So then you do this a bunch more times because you're a graduate student and you do a lot of labor, and you take a lot of samples. And this comes together into the complete XRD results from this study. So I've divided this into results for Last Chance Lake as well as Good Enough Lake, and then in each respective lake, the sediments and the salts being the evaporites around the lake shore as well as the precipitates in the lake. On the left-hand side, we have all the different mineral phases we've identified. So in the sediments, the main phases of interest were these feldspars, both plagioclase feldspar as well as alkali or K feldspars, as well as dolomite, those calcium carbonates, and mica, the clay minerals. We're also seeing some thermonatrite, that sodium carbonate, in the Good Enough Lake sediments, but not in the Last Chance Lake sediments. And then the main mineral phases we're seeing in the evaporites or the salts are those sodium carbonates, both thermonatrite and trona, as well as berkite, that sodium carbonate sulfate. Quick word about hydrated minerals. We only detected thermonatrite, which is sodium carbonate with one water molecule, in the XRD patterns after sample preparation. However, previous studies of this area have identified natron salts as the predominant phase. Natron is just sodium carbonate with 10 water molecules. And so if the relative humidity is below 60% at 0 degrees Celsius or 70% at room temperature, then natron will lose its water and turn into thermonatrite. And so we're just anticipating that's what happened in our samples here, since the relative humidity in indoor environments is around 50%. So you can see this plot on the right-hand side from Haynes et al. Showing natron here turning into thermonatrite when you've decreased relative humidity and increased temperature. So in summary, we found that the evaporites, or the salts, are dominated by sodium carbonates, sodium carbonate sulfate, and sodium chloride, demonstrating the predominance of that sodium ion in the lakes, whereas the sediments are dominated by carbonates, both dolomite and anchorite, as well as feldspars, plagioclase and K-feldspar, quartz, pyroxene, and clay minerals. However, the big takeaway was we found no calcium phosphate, which is that apatite I talked about earlier, in any of the samples. And this was confirmed by ICP-MS data, showing very low abundance of phosphorus in all of the different samples we've taken. So it's not just an XRD fluke, it's also backed up by elemental abundances. These results are consistent with the hypothesis that calcium carbonates precipitate early in the mineralization sequence of these lakes, thus decreasing the dissolved calcium concentrations and allowing phosphate to accumulate to high concentrations instead of precipitating out as apatite, which is that calcium phosphate. So phosphate's accumulating to high concentrations in solution, and that's great for that prebiotic phosphorylation that you need very high phosphate concentrations to get that incorporation into your nucleotides and the potential origin of life. So these could be really good environments for analogs for Hadean Earth lakes where life started. And that's it.
Thanks, Kimberly. We have plenty of time for questions. I have a quick one for you.
Yeah.
Do you know how Goodenough Lake was named?
I think it was something about westward expansion, and when they got there, they were like, oh, this is good enough, and then they turned around and went back east.
Yeah, I was just curious, because when we were in Australia, there was a lot of strange lake names out there, like Dead Kangaroo, Pete's Piggery, and we didn't really understand like the history of them, but
yeah.
Anyway.
There were a lot of jokes in the field about, oh, it's our last chance to get our last chance sample and stuff like that.
Hi, I'm Ellie from CU Boulder, and I was wondering if so I know you said your sediments are plage, dolomite, mica, and feldspar dominated, and I was curious if you would think that the similar pattern that you saw here would happen even if your soda lake was hosted by a different type of base rock, essentially. Like if we change instead of basaltic or things like that, like do you feel like the same pattern would hold in terms of the precipitation of the evaporites?
Yeah, these lakes are very dependent on the host mineralogy, and so you wouldn't expect to see the same aqueous chemistry in a different host environment. And that's one of the reasons why this environment is so interesting, is because of that plagioclase base rock causing this very specific aqueous chemistry. So even just 100 miles nearby is an incredibly sulfate-rich lake that people study for different reasons. So slight change in geology, big change in aqueous chemistry.
Hi, really interesting talk. I have kind of two questions. You mentioned that you collected samples seasonally and did sediment by depth measurements. Do you see any variability in your mineralization based on seasons, and was that reflected in any depth transect?
Yes, we hoped we would see more variation, but we didn't. The only variation you really saw was that you could say, and maybe this isn't even a statistically significant conclusion, is that you might see more dolomite at the top of the sediment core, so right in the interaction zone with the water. You're getting less dolomite at depth, which makes sense for calcium carbonate precipitating out of solution, whereas at depth in the sediment cores, you're getting more of those feldspars, which is just the host rock, but not as much in terms of seasonal variation.
Hi, I'm Shiva Agrawal from Western Michigan University. Can you go 2 slides back? Yeah, so you have data for, I think, nacolite and thernandite, which has uncertainty higher than the data. So is it normal, or how can you explain this?
Sorry, could you say the last part again?
So the uncertainty in the data is higher than the value? So can you
Yes.
explain this? Is there
Yes, because a lot of these samples only have these minor phases in a couple of the samples. And so there's just not very good counting statistics. We're talking about maybe 3 out of 100 samples or something that have these minor phases. So, yeah.
Taylor Plattner at Georgia Institute of Technology. This is really cool. I had no idea that these lakes were so high in phosphate. I know a couple of people that have studied like Last Chance Lake and then the Basque Lakes. I was curious because you were saying at the end, interesting in terms of like the origin of life. Have you thought about? Actually, I have a couple questions. Have you thought about like looking at what may be preserved in these salts, and I also have a question on, I know you did XRD, do you plan on doing any other analyses with your samples?
Yeah, so I guess your first question about if we're studying the present life in the lakes? Yeah?
Or preservation or anything.
Yeah, so at a macroscopic scale, when you go there, it's really interesting because you see all these brine flies that are just encrusted in the salt, which is kind of freaky because in the summer you're like encompassed by flies, and then in the winter it's like a fly cemetery and there's just a bunch of dead flies on the ground. But in a more astrobiology sense, there are other teams at, I think it's, university in Canada who are studying the current microbiology in the ice because there are living microbes in the ice in the winter. And so we're not necessarily doing that work, but there are colleagues who are. Wait, what was your second question? Yes, okay. So my section of the work was a lot about the mineralogy of the sediments and the evaporites, but my colleague Sebastian Haas did a lot more of the water chemistry. And so we're submitting a paper now, and hopefully you'll be able to read that and hear all about his work as well.
Thank you very much, Kimberly.
Yeah.